Hi, and welcome to our lesson 2-3. For the next few days, we're going to be talking about polynomial functions and their graphs specifically today, and then several days spent on finding roots or solutions for polynomial equations. So today our focus though is going to be on graphs. So we want to start by introducing what exactly a polynomial function is, and there are two criteria. In order to be considered as a polynomial function, you have to have coefficients that are real numbers. So coefficients are real numbers. And secondly, the exponents have to be positive integers. So, positive integers. So if you think about that, an integer is a number that has no fractional part, a whole number, if you will, positive or negative. But this says you have to be positive, so positive whole numbers. Coefficients have to be real numbers. It does include fractions, irrationals, like square root of 2 or whatever. That's okay for coefficients. Exponents have to be positive integers. And with that in mind, I have 1, 2, 3, 4, 5, 6 functions that I'd like you to take a quick look at. I'll look at the first one with you, and we're going to decide if they are or aren't polynomial functions. The g function that's shown here, one coefficient is -3, which is a real number. The other coefficient is square root of 2, which is also a real number. So we are good there. Exponents, positive integers. Well, this one's 5, and that is a positive integer. This one, of course, isn't shown, but it's assumed to be 1, and that also is a positive integer. This is a yes. This one is a polynomial function. I'm going to ask you to do the same thing for the other 5 functions shown. So let's pause that video, decide whether we are or aren't. Alright, here are my answers to that question. The h function is not. Although the coefficients are both real numbers, that's okay. That having the x under the radical, that's the same thing as x to the 1/2 power, and that's not an integer. So this is not a polynomial function. This one is a yes. Only exponent is 1, x to the first, so that's a good. Here, no. Again, we've got that 1/2 power. Here, not a polynomial function. Even though it shows this x squared, that is positive, the exponent is positive down there in the denominator. If you were to write this all on one floor, like if you were to simplify it, if you will, this is the same thing as -3x to the -2nd, and that is not a positive integer, so this is not a polynomial function. The last one is a polynomial function. The exponent is fine, and the coefficient is a real number, so we're good there. The deal with polynomial functions that have degree 2 or higher, and that would be an exponent, a power of 2 or higher, they have graphs that are smooth and continuous. You should never, ever, ever have to lift your pencil to draw the graph of a polynomial function. Smooth and continuous. And we have a couple of examples of polynomial functions here. We're going to begin our discussion of graphing by talking about the leading coefficient test. And what that does is tell you about a polynomial's end behavior, it is called. End behavior. And what that means is what is happening to the function, end behavior. What is happening to the function as x gets extremely small or extremely big. As you can see, there are 4 types of end behaviors that are possible with polynomial functions. So what I'd like to do is tell you which kind of equations lead to which kind of graph, and then how to describe those end behaviors. As you'll look at this one, when x is getting small, y is small as well. When x gets big, y is big as well. That comes from having a positive leading coefficient in a function whose degree is odd. So a 3rd degree or 5th degree polynomial with a positive leading coefficient gives us this type of end behavior. To describe that, there are 2 ways. You can use just the arrows down, up, and that is wonderful for me. However, the more mathematical way of expressing it is this way. As x goes to negative infinity, which means it gets really small, y goes to negative infinity. As x goes to positive infinity, when x is getting big, y gets to positive infinity, also big. Okay? Down, up, down, up. This next graph is showing a negative leading coefficient with odd degree. So again, a third degree polynomial, a fifth degree polynomial, a first degree polynomial for that matter. The end behavior there is up, down, exactly the opposite, right? And you can see that played out here. The last two functions here are even degreed functions. And you will notice that in this one we have up, up end behavior that comes from a positive leading coefficient in an even degreed function. The last one, a negative leading coefficient in an even degreed function. And if you think about that, think parabola, that's, you know, with the negative out in front that flips it over. That's exactly what's going on here. That end behavior is down, down. When x gets really small, y is very small. When x gets really big, y is really small. Down, down end behavior. So now we've got one for you to talk about end behavior. Remember, that's predicted by the leading coefficient. So you have to think, if this were all multiplied out, what the leading coefficient would be and decide about its end behavior. Will you pause the tape and do that now? Right, here's my thinking for that. 5 powers of x would happen, 3 here, 4 and 5, if you were to multiply it all out. The leading coefficient is a positive 2. So we are talking about an odd degree function, 5th power, with a positive leading coefficient. That puts us right here, and our end behavior would be down, up, or here, down, up. Good. We want to talk next about finding the zeros of polynomial functions, and you'll recall that zeros are where the function, their x values, where the function crosses the x-axis. Those are the zeros of the function. And one way to find them is algebraically. Set the function equal to 0, solve for x, it says. So if we were going to find the zeros of this one, we would say that 0 is equal to x to the third plus 2x squared minus 4x minus 8. Now, ladies and gentlemen, with those powers of x's, we're not going to be able to say undo what's been done to x. We're going to have to use some different strategy. And I'm going to ask you to think about factoring. I'm looking at this function in two pieces. What's the greatest common factor here? What's the biggest thing both can give up? Now you think to yourself, this has 3 powers of x, that has 2, so x squared is the greatest common factor. I'm going to bring that out to the front, so I'm doing the reverse of the distributive property here. If I divide x cubed by x squared, I'm left with an x. If I divide 2x squared by x squared, I'm left with a plus 2. So there's that part. Now I want to have you take a look at this. Greatest common factor for the rest of this function is negative 4, I believe. Because if we divide here by negative 4, we get x. If we divide here by negative 4, we get plus 2. And you'll notice now that we have two factors that are exactly the same. That means the greatest common factor from here is x plus 2. If we divide x plus 2 out of this one, we're left with an x squared. If we divide x plus 2 out of this one, we're left with a minus 4. And folks, I'm here to tell you that this factors, x squared minus 4 factors. So I'm going to have you pause the video. I want you to do the x box. We're going to try and factor this guy. Very good. I did my x box over here. In the x, I put the negative 4 on top because we have to find things that multiply to make negative 4 while they add to make 0. Only possibility is negative 2 and 2. So then I move to the box. I already put my x squared in the top left, my minus 4 in the lower corner, and then these guys, negative 2 and 2, go into the boxes here. Once you have that all in place, then it's take out a greatest common factor. So an x comes out of that top row. If this is x, then this must be x also, because together they had to multiply to make x squared. If this is negative 2x, then what has to be up here is negative 2, because these two things, x and minus 2, have to multiply to make it, etc. So the two factors from that last part, x plus 2, x minus 2. I cannot, folks, I would not be doing my job correctly if I did not remind you, this is a common factoring pattern. When you see something that's like that, a squared minus b squared, that always will factor the same way. A plus b, a minus b. Square root of one, square root of the other, once with a plus, once with a minus. That is called a difference of squares, and it's something that you will see often when you are factoring. Difference of squares. Alright, so we're almost there. We have this thing factored. To find the zeros, we have to set each parenthesis equal to 0. So doing that, if x plus 2 is 0, then x must be negative 2. And we have that one coming up twice. That negative 2 is a root twice. We'll list it twice, but then when that last parenthesis, if x minus 2 is 0, then x must be 2. Another way of writing this is saying that you have x equal to negative 2 with a multiplicity of 2. That just means it's a root that happens twice, and you have 2. I'm going to ask you to come down here and just put that little information in, because that's where it's supposed to go. A 0 is said to have multiplicity if it occurs more than once. Very good. We have one that we're to find all the zeros on using our calculator. That is a thing that's very important to me, so I'm going to go over here and grab my calculator. I have my calculator, and I have our function plugged into the y equals x to the 4th minus 4x squared. I tried a zoom 6 window. That is the standard window, and this is a 4th degree function even. I should have up, and behavior. So yep, this is all we're going to get. This is the important stuff in this particular function. We are to find all the zeros, it says, using second, trace, and root, or 0. So second and trace. You've seen me do this before. I'm going to ask you to pause the video. You go after those zeros yourself, please. I use my calculator's second, trace, and 0 functions, and I came up with this. X is equal to negative 2 and 2. But when I went after the middle one, a weird thing happened. I want to show you. Second and trace, and I'm going to go here. I want to go for that middle 0, which I think is 0. In fact, I'm pretty sure of it, because when I trace, I hit right there. So I know that that's a 0, but I want to show you what happens when you try to go after it using the root function. See how long it's having to think about it? And it says no sign change and quit. So I am gonna go ahead and do the quit function and tell you that the reason that happens is when this calculator is looking for a 0, it's looking for the sign on y to change from positive to negative, and it doesn't right here, because that 0 at 0, by the way, with a multiplicity of 2, that's because it hits 0 on the way up, and it also hits it on the way down. And folks, that's not a professional thing to say, but I do know that a 4th degree function has to have 4 zeros. One of them is at negative 2, one's at 2, and that 0 in the middle, again, it's a bounce spot in here, and that means that it's a 0 twice. When you see that bounce, that means there is a multiplicity of 2. In fact, that's what this next slide says. If a 0 has even multiplicity, the graph hits the x-axis and then bounces back. If a 0 has odd multiplicity, the graph goes through the x-axis, changes from positive to negative or negative to positive, goes through the x-axis. Y, the sign on y, changes from positive to negative, or vice versa. This says that we should find the zeros of this function. Negative 4 times the quantity x plus 1/2 squared times the quantity x minus 5 cubed. Oh my, please don't start multiplying that. We already are in factored form. The negative 4 has no effect on the zeros, so I'm going to say, if you think about it, you could divide. If you make this 0, you can divide by negative 4. It won't change anything. So what we need to do is set each parenthesis to 0. So 0 is equal to x plus 1/2. And if you solve that for x, you know that x has to be negative 1/2. That happened twice. There were 2 factors like that, so that has a multiplicity of 2. X will also equal 5 with a multiplicity of 3. Okay? 3 times 5 is a 0. Now, the last little point that I'd like to make is that a table can help you to find those zeros. The intermediate value theorem states, and so there's probably a way better way to say it mathematically. I'm going to just give you my words. When the sign on y changes from positive to negative or vice versa, when the sign on y changes, you've passed a 0. Okay, the last activity is asking you to use a table to decide between which integers this function has zeros. I'm going to ask you to work with me on the calculator on this one. I have the function entered into my y equals. I want to look at a table, and I know we did this in the very first lesson, but I just in chapter 1, but I'd like to just run through it with you again quickly. It's second and window for table set. I'm not sure where the zeros are, but negative 5 is okay for me to start. I'm having my table change in units of 1. To look at a table, second, and graph. And what we're doing is trying to find the integers between which this function has a 0. And the intermediate value theorem says when the sign on y changes from negative to positive, you've found a 0. So one of them will happen between negative 3 and negative 2. Somewhere between negative 2 and negative 3 is 1, 0. See here, the function grows and then it gets small, but it never gets under 0. So we've found the only pair of integers that surround a root when we found negative 2 and negative 3. You can verify that by looking at the graph. And there is a graph of this picture. All right, we'll ask you to get out there, try that you try, and we'll talk about it in school tomorrow.